We started chapter 6 on Monday, right after the Thanksgiving break, and it's called Random Variables. So let's skip the definition for a minute and take a moment and write down all the ways our scenario could play out if I toss a coin 3 times. So for example, first I could get heads, heads, heads. So maybe hit pause, write out all the ways this could play out. And it's called the sample space. We've done this kind of thing before. This is nothing new. All right, so we may get that. We may get that. Or that. Or maybe 2 tails. Or maybe all tails. Oops. And one way to check if you've got them all is, I'm flipping the coin 3 times. So there's 2 ways on the flip, two ways it could play out on the first flip, 2 ways on the second, 2 ways on the third. Multiply, and there are 8 possible outcomes. All right, hopefully that's easy. Probability of each, well, hopefully you see it's 1/8. One way to do this is, we have 8 outcomes up there, and if I'm tossing a fair coin, then any of the 8 have an equal chance. So if all equally likely, then it is 1 over total possible outcomes. That says outcomes right there. Maybe you don't see that it's equally likely because you're sitting there thinking, well, I think it's more likely to get maybe HTH than HHH. Which I sympathize because it looks like getting 3 heads in a row would maybe be rarer than the others. But that's you got to be careful with how you think about that because remember our coin is independent. So first flip is 1/2 for either option. Next flip is 1/2. Next flip is 1/2. So, So any one of those is 1/8. Any one of those outcomes is 1/8. Where it changes is when we define a scenario. So getting 1 heads, that's different than getting all 3 heads or 2 heads. But that's because there's multiple ways it can happen. So down here, when it says create a probability distribution, it is really saying create a table. And that's when likelihoods possibly change. So I like to make a sideways t-chart. Something like this. The bottom row is going to be the probability of each x. Now they define x for us. That is our random variable as is defined at the top. But in this scenario, it is number of heads. So before we talk about random variable, let's count up the possible ways this could play out. If I'm counting possibilities like number of heads when I toss it 3 times, I might get 0 heads. I might get 1 head. I might get 2. And I might get 3. If you're still confused, attach the scenarios to it. So this might be this is tails, tails, tails. This is tails, tails, H, tails, H, tails, and H, sorry, I'm writing over that, tails, tails. This is H, H, T, H, T, H, and THH. And then this is all heads. And I'm just organizing my scenarios. That's basically all we're doing here. But I skip that opening definition because it confuses people. This right here at the bottom, I believe, is a better definition of a random variable. If I have some kind of chance situation and I define X or Y or Z, whatever letter they want to call it, and I define a scenario, now I have a random variable. So it's a chance process, and I'm coming up with some kind of numerical outcome. All right, now let's attach probabilities. I see only one way out of the 8 that I get 0 heads. I see 3 ways out of the 8. 3 ways out of the 8. And I see 1 way out of the 8 for 3 heads. And one way to check that I did it right is these should all add up to 1.0. Hopefully that made sense. This table is a probability distribution. All right, moving on. We're going to change gears. Well, kind of. We're going to define discrete and continuous. The problem we just now looked at was discrete, because it said number of heads. Remember, continuous is a measurement. We talked about this months ago. So we'll look at continuous variables here in a little while. Right now we're going to work with discrete. Remember, each probability needs to be between 0 and 1. And they all need to add up to 1.0. So we have this scenario here, APGAR scores. Long story short, when you were born, you get a score, an APGAR score, based on 0 to 10. And it works with reflexes and how you respond to different things. I have a scary story I shared in class about my youngest and how she had seemed like a near-death experience. Maybe the doctor would say otherwise. And she had a horrible APGAR score at first because the cord was around her neck and blood flow was lacking. But then they gave her a few minutes and blood was flowing very well, and she passed she had a high APGAR score. So APGAR score, higher the better, the more healthy the baby. And we have our table that someone has made for us. I would say this table is impossible to create on our own just from what they described. We couldn't do it. They would have to give us data to be able to create that table. So sometimes it's nice and they give you the probability distribution in advance. And here is the definition of our random variable right here. And they want us to show that this distribution is legitimate. So I'll save you a little time, and if you type all of them in, they should add up to 1. So we could write 001 plus 006, save a little time and write ... then the last one, and that equals 1.0. Please, if this is an FRQ, type it into your calculator and check. But when you're writing it down, you just have to write that you know what you're doing, that they all add up to 1. It's a timed test. You got 11 things right there. Feel free to summarize like that. So it is legitimate. We need to make a histogram now. And this is discrete data. So I'm going to do a bar for each APGAR score. So I make a dash for each one. So I made my graph. Sorry, we had a big jump there. I didn't want you to have to watch me make it. And I made one of the bars. So some things to notice. It's discrete. I need to give it a width of 1 because it's based on that calculus idea of area under the curve being probability. So if I get the area, it's also geometry. So if I get the area of that bar, I go width times height, and it is 1 times 0.437, which is 0.437. That's the likelihood of 9. So technically that goes from 8.5 to 9.5. Some statisticians don't really like this method, and they prefer us to do these vertical bars like this. And they have an argument, because if we're talking about discrete, it's impossible to get, say, 9.1 or 8.8. But yet it doesn't work out geometrically. It's all really annoying, and they all argue about what the correct method is. I prefer this. Our textbook shows it this way. I would recommend doing it this way. So here is the rest. Hopefully that makes sense. Some of those bars may be off a little bit, but I think you get the right idea. I mean, those to the left should probably be shorter. Maybe my 9 should be shorter. Yeah, looking at it, it looks like it's a little too high, but I think you get the right idea. We see some negative or left skew here, with typical being 8 or 9, and it ranges from 0 to 10. Okay, moving on. We have another question on this. They define a healthy baby as 7 or higher. So I want to write it like this: x greater than or equal to 7. And I need to add up all those probabilities. So take a minute and look at your table. And it looks like probability of 7 is 0.99. You might need to rewind to see these numbers again if you don't have the handout. So add all those up, and I get 908. So I would say probability of a healthy baby is 90.8. You know, there's a chance at being less, chance at being more than 7, but they define healthy as that. So this is a very convenient thing, because you take something that's statistical and science-based, and then we can attach some real language to it that the general public may understand. That's the importance of statistics. Can I translate it to the general public? All right, one last thing. We have a new formula we need to work with here, and that is expected value. So I need to use this table right here to do the expected value, and I promise you it is not complicated at all. So I'm going to go back, but notice a key word here. This is the mean or the expected value of discrete random variables. I'm going to go the first x times its probability plus second x times its probability, and so on. So that's all it's saying. This is typed on your formula sheet. All right. Notice they say find the mean of the random variable x from APGAR scores. I would guess, I'm going to use this table right here so you can see it. I bet they are going to reword that as what APGAR score is expected for a baby, or maybe they just leave it like that. What is an expected APGAR score? Maybe that sounds a little better. But in the end, I'm going to go E of x equals, now watch the table and watch what I write. We're going to go 0 times 0, 0, 1 plus the next x, 1 times 0, 0, 6. I'll do another one. Plus 2 times 0, 0, 7. I think you get the idea. I need to type them all into my calculator, but let's do some ... right here and go 10 times 0.53. All right, when I do all of that, type it all in, maybe hit pause and type it in on your own. And I get 8.128. And it said to interpret this on average. We expect babies to have an APGAR score of 8.128. All right, I hope that made sense. This formula is typed on your formula chart. Please check out the optional assignment. It'll help you out. You need to practice this. Please, please. See y'all later.